Hello, and welcome to our TypeScript Crash Course. In this series, we'll teach you TypeScript's fundamental concepts, with simple examples. We'll cover everything from scratch, but because TypeScript is built on top of JavaScript, you'll need to be familiar with basic JavaScript concepts, like variables, objects, and functions. Let's get started by defining TypeScript. TypeScript is a programming language built on top of JavaScript. That means it contains all the elements of JavaScript but adds some really useful features. The main one, though, is static typing. In programming, we have two types of languages, static and dynamic. In statically typed languages, we define data storage with explicit types. For example, if we declare a variable's type as string, it'll only be able to store that type, nothing else. If we try to assign a different value to it, the compiler will raise an error. In a dynamically typed language, the variable's type is determined at runtime based on the value inside it. So we can define the variable with a number, but later change it to something else, like a string. While dynamic typing gives us a lot of flexibility, it's not safe. If we pass the variable to a function that expects a number, our application would misbehave. TypeScript tries to solve this problem by allowing us to define types for our variables, function parameters, classes, etc. Saying allows us is important here, because using any TypeScript feature is completely optional. We can have a TypeScript file with regular JavaScript code, and everything would still work just fine. That's because TypeScript code is converted into regular JavaScript in a process called transpilation, which we'll demonstrate a little later. For now, let's set up our development environment in the next lesson. The only thing TypeScript needs to work is its compiler. We can easily install it with a package manager like npm. npm is bundled with Node.js, so head over to nodejs.org and grab the LTS version. Once your installation has finished, open a new terminal or command prompt, depending on your operating system. To install the TypeScript compiler, we'll say npm install-g TypeScript. If you're on a Mac or Linux, you may need to add sudo in front of the command. We can confirm the installation by running tsc-v. It doesn't matter if you install a later version, everything in this series will still apply. Lastly, we're going to use VSCode as our IDE. You can use whichever IDE you prefer, but if you want to use VSCode too, you can download it from code.visualstudio.com. We're also going to install the live server extension to be able to launch a local development server with hot reloading. We'll leave a link to it in the description below. Alright, let's get started with our first TypeScript app. We'll change directory to the desktop and make a new folder called First App. Then we'll do code, space, and a period to open the project in VS Code. From inside the editor, create a new file and call it index.ts. Now, earlier we mentioned that we can have any JavaScript code in a TypeScript file, and it'll be valid TypeScript code. So we can do something like define a greeting message, then alert it in the browser. But, because a browser can't understand TypeScript, we have to compile the code into JavaScript first. To do that, we run the TypeScript compiler. In the top menu, go to Terminal, then choose New Terminal. From there, type tsc and the file name you want to compile. In our case, that's index.ts. TypeScript will transpile the code into valid JavaScript and store it in a file with the same name. But, if we open the file, you'll see the variable's been declared with var instead of let. By default, TypeScript compiles with ES5 syntax, but we want our code to be more modern. Luckily, we can configure the compiler to target a newer JavaScript version. Let's open the terminal again and run the command tsc:\init. This will create a new configuration file called tsconfig.json with some basic compiler settings. The first setting we want to change is the target, that we'll set to ES6. The next setting we want to change is root dir, under the modules section. It specifies the directory that contains our source files. We'll remove the comment with Command or Control/ and set it to src. Then we'll create the folder in the Explorer pane and drag our TypeScript file into it. Let's also delete the JavaScript file. We'll generate a new one in a second. To specify the folder where we want the source files to compile to, we use the outdoor option in the emit section. We'll set it to dist and create the folder in the Explorer. From now on, we don't have to specify the file name when we compile, we can just write tsc. If we open the generated JavaScript file, we'll see it uses the new syntax. To test it in the browser, we'll create a new index.html file in the dist folder. Inside it, we'll type an exclamation point to bring up emit, then press tab to create some HTML skeleton code. In the body, we'll do a script tag that links to the index.js file. And because we have the Live Server extension installed, we can just right-click the file and choose Open with Live Server. If we switch over to the browser, we'll see the alert with the greeting message, so everything works like we expect. But we haven't used any of TypeScript's features yet, so let's go back to the editor and give our variable a type. To do that, we add a colon after the name, then specify the type. In this case, we want the type to be a string. Now, if we try to change the greeting to something else, we get an error. And if we hover over it, we can see that a number isn't assignable to a string type. So we're getting errors before we even compile our code, saving us a lot of time. Let's remove this and compile the code again. But this time, we'll add the watch flag with --watch. The compiler will continuously watch for changes and recompile the file when we save, so we don't have to do it manually every time. If we switch over to the browser, the alert still shows the message, so everything works as it should. JavaScript gives us built-in types like string, number, boolean, object, etc. TypeScript builds on that system with a bunch of extra types. Let's take a look at the built-in types first, starting with numbers. The number type represents both integers and fractals, and uses number as the keyword. It also supports hexadecimal, octal, and binary values. A boolean is a named constant that represents the logical values of true and false. They're technically numbers themselves, where true is 1 and false is 0. If you're coming from another language, like C#, keep in mind that you have to use boolean as a full keyword and not just bool. A string is an array of Unicode characters combined to form words or sentences. Strings can be wrapped in single or double quotes and uses string as the keyword. Let's declare a variable called empty, without a value. If we hover the mouse over it, we can see that the compiler assigned any as the type. We can also specify it explicitly. Basically, the any type tells the compiler to skip type checking on the variable. So we can assign something like a number to it, and that'll work. Or we can assign a string, and that'll work too. But that defeats the whole purpose of having type checking in the first place. We want to avoid using any as much as possible. Luckily, there's another type called unknown, that's similar to any, but forces us to do some other sort of type checking. We'll cover the unknown type when we talk about type narrowing. For now, just keep in mind that it exists, and it's preferable to any. Now, let's move on to user-defined types, starting with arrays. In JavaScript, we can define an array with different types of values. But in TypeScript, the entire array has to be the same type. To annotate it, we specify the type, followed by a pair of square brackets. Of course, now we'll get an error with the string, so let's fix it. But what if we need an array of different types? For that, we use tuples. A tuple is a fixed-length array where each element has its own type. And because it's an array, we still use the square brackets, but this time we specify the types inside it. Let's say we want our user to have an ID and a name. We'll do a number for the user ID and a string for the name. Then of course, the values have to match the types in those indices. It's important to note that tuples have a fixed length, So if we add a third value, we'll get an error that says the tuple only allows 2 elements. So we can't initialize a tuple with more values than we defined in the annotation. But a tuple is just going to compile down to a regular JavaScript array. That means we can do users.push to add another value and the compiler won't raise an error. Hopefully this will be fixed in the future, but for now, just be careful when working with tuples. An enumeration is a set of named integer constants. They allow us to create a set of symbolic names that map to known numerical values. The easiest way to understand an enum is to use a boolean as an example. A boolean allows us to write the words true or false instead of the numbers 1 or 0. An enum is a custom variation of that, where we declare our own words to map to numbers. To define an enum, we write enum, then the name in Pascal case, then a pair of curly braces. Inside the braces, we define our values also in Pascal case, separated with a comma. By default, TypeScript assigns a numerical value to each of the enum's members, starting at 0. So in this case, Monday would be 0, Tuesday would be 1, and so on. But we can also assign our own numbers to the member, or something like a string. Let's say we want the values to be a string of the day's full name. If we do that, we'll have to explicitly define a value for each member in the enum. If we log it to the console, we can see that the enum is basically just an object with key-value pairs. So, we can define a variable and set the enum as its type. Then we'll use dot notation to access a day of the week as the value, and log it to the console. If we take a look at the generated code, we'll see the JavaScript implementation. It seems a bit complicated, but it's just to allow the enum to be extended. As a quick tip, we can add const in front of the enum. And if we look at the generated code again, it doesn't have the object anymore, just the variable where we use one of the members. Okay, let's move on to functions, and also take a look at how to solve common problems related to them. In TypeScript, we have to add a type for each parameter in the function header. In this case, we know the values we're expecting are going to be numbers, so we can annotate it accordingly. If we mouse over the function, we can see that it implicitly returns a number value. While TypeScript is smart enough to figure out the return values type, it's still a good idea to explicitly annotate it after the parameter list. But what if we have a function that doesn't return a value? Let's change the function to log the addition to the console, instead of returning it. TypeScript will raise an error on the type, because even though we're outputting a number, the function doesn't actually return anything. To fix the error, we change the return type to void. Now, let's say we forgot to add y in the console log. As you can see, TypeScript doesn't show us any errors for unused parameters. It's not because TypeScript can't check for it, it's just not turned on by default. So, in the tsconfig file, we want to find the No Unused Parameters option and uncomment it. Now, if we go back to our code, we'll see that the compiler raises a warning. Let's remove it from the parameter list and define it in the body. Again, TypeScript doesn't warn us that we have an unused variable. So, we'll go back to the tsconfig and uncomment the line that says no unused locals. If we go back to the code, we'll see the warning. Okay, let's revert the function back to how it was in the beginning. Now let's say we want to restrict the function to not allow any negative returns. So we'll say if x and y is greater than 0, only then return the sum. But now we're getting a new error that the function doesn't have a return statement. So what happens is that we return the sum if it's above 0, but because there's still a code path open, JavaScript returns undefined, and undefined isn't a number. If we remove the return type, the compilation error will be gone, but the function still has the problem. So, let's fix the problem and say, if x and y is not greater than 0, just return 0. Then in the function call, we'll change the second parameter to be -2. And there we go, no compilation errors, and the number shows 0. Another useful feature in TypeScript is that we can add default values to function parameters. A default value makes the parameter optional, so we don't have to specify an argument in the function call. To add a default value, we just assign it to a parameter in the function's header. Now if we invoke it again, but this time without an argument, it shows the default greeting. When we're working with objects, we assign values to properties with the colon operator. But TypeScript uses the same operator to specify types, so we can't annotate properties like we do with variables and function parameters. Instead, we go after the name and create a type object, where we specify the property name with the type as its value. So basically, we're describing what the object should look like. We can do the same with methods. We need to describe the parameters it's going to have, their types, and the return type. So we'll have a method called greeting, with a message parameter as a string, and the return type will be void. Of course, we'll also have to add it to the initialization, so we'll say, greeting, message as a string, and we'll just log the message to the console. To complete the demonstration, we'll log everything to the console. Okay, everything works as expected, but there's some issues here. The main problem is that if we want another user, we have to repeat the object structure, so we end up with duplicate code. TypeScript allows us to create a type alias that allows us to define a custom type. So we'll go at the top and say, type, then the name of the type in Pascal case, so user, and then an object. Inside the object, we define all the properties and methods that a user should have. In our case, we'll use the ones we've already defined. So we'll select the 3 lines, and press Alt and the up arrow, to move them into the type. All we need to do now, is to annotate the object with the user type. If we save and take a look in the console, everything still works fine. But now we have a single place where we define the user, so it's easier to read, easier to modify, and we can reuse it anywhere we want. With union types, we can give a variable, alias, or function parameter more than one type. Let's define a variable and annotate it with a number, or a string. We use the pipe operator to separate the types. Now we can do something like, union is 10, and the compiler won't complain. In fact, let's log it to the console. We can go back and change union to a string, and it'll work just fine. But there's a problem. Let's remove these, then change the variable to an alias. Now let's define a function that has a single parameter with the union as its type, and log it to the console. We'll also invoke it below, with a string argument. If we save the file, it logs the name just fine because a console log is valid for both types. But what if we want to change the string to uppercase? That's something that can only affect the string, we can't uppercase a number. To fix this problem, we use what's known as type narrowing. We have to narrow down what action to perform for which type. So we can say, if the type of the parameter is a string, make it uppercase. And we'll add a second function call with a number to help the demonstration. If we save and take a look in the console, the name is all caps, and the number shows without issue. Now let's take a look at literal types and how unions can help us with them. Literal types allow us to limit the values that we assign to our variables. All we need to do is annotate it with a value instead of a type. If we try to initialize the variable with a value other than 6, we'll get a compiler error. If we want more than one value, we can use the union operator. And of course, we can also separate them into a type alias, then annotate the variable with it. It should be noted that while we're using numbers here, literal types can also be strings. When we discussed the any type earlier in the series, we mentioned that it's preferable to use unknown instead. The problem with any is that it completely opts out of type checking. We need something that can still do type checking, even when we don't know what the type will be. Unknown means that a variable's type isn't known, and TypeScript doesn't allow us to use an unknown type unless we cast it to a known type or narrow it. As an example, let's declare a variable with unknown as its type. If we try to square the variable in a console log, the compiler will raise an error that the type is unknown. Let's fix the error with type narrowing and say, if the type of X is a number, then you can square it. And there we go, the error is gone, and the console shows the correct value. Okay, that's it for the fundamentals. Next we'll take a look at more advanced concepts, starting with object-oriented programming. Object-oriented programming, or OOP for short, is a popular approach to solving problems in programming languages. Object-oriented programming is when we treat data and behavior as a single unit. Basically, we try to model our application after entities in the real world by using classes and objects. As an example, let's consider a database of users. Every user has attributes, like a name, an age, an email address, etc. They also have functionality available to them, like changing their password or updating their profile picture. We combine these attributes and functionality into a class, and every instance of a user will follow this pattern, just with different attributes. For example, an array is a class. When we create an array, we're actually creating an instance of the array class, in this case, an object called shopping list. Once we have the object, we have access to the properties and methods in the array class. That's why we can do something like shoppinglist.length or shoppinglist.push. We can define as many arrays as we need, and each of them will always have a length property and push method, no matter what values are inside. To declare a class, we use the class keyword, followed by a name in Pascal case, and then a code block with curly braces. Usually, we name classes in the singular. For instance, instead of naming a class cars, we call it car. Inside the code block, we'll add a property called name, of type string, with an empty string as its value. Below that, we'll add a method called walk, and we just let it do a console log. Typically, we'd use a constructor for the attributes, but for the sake of simplicity, we'll do it this way first. To create an object instance of our class, we use the new keyword, followed by the class name, and then parentheses. Okay, now that we have an object, we can access its members with dot notation. So we can do emp1, then a period, and we'll see the properties and methods available to us. Let's choose the walk method. If we save and take a look at the console, we'll see it prints out the text. Let's also assign a value to the name property. So, we'll do employee1.name equals John. And to confirm that it worked, we'll do a console log. Okay, it works, but there's kind of a problem here. Classes often have a lot of properties, and going through the process of assigning a value to each one every time we create an object is tedious. This is where constructor methods come in. A constructor is a method that allows us to initialize an object with values when the object is created. Let's remove these and go back to the class and remove the empty string value. Now we'll get a compiler error saying that the property has no initializer and is not definitely assigned in the constructor. So let's create the constructor method below the attributes, then add the parameters we want to initialize with values. In this case, we only have a name, so we'll add name is a string. Inside the method we'll do this, to reference the calling object, and the name attribute. Then we'll assign the name parameter to it. Actually, to make it clear what's going on, let's set the parameter to pname. Okay, now we get a new error where we instantiate the class. That's because the constructor wants us to add a name in the parentheses. So it's just like a function call, but the constructor dictates what arguments we need. We'll do John as the name, and to confirm that it works, we'll log employee1.name to the console. Okay, the name in the object was initialized with the value we gave it. Typically, the constructor's parameter names are the same as the property names, so let's quickly change pName back to name. In TypeScript, we have modifiers that we can apply to our properties. For example, let's say we have an ID property that should never change. At the moment, we can go inside our method and do this, .id equals -1. Similarly, we can go outside the class and modify it on the object. This could lead to bugs or security issues in our application. To solve this problem, we use the read-only modifier. So we go in front of the ID property and say, read-only. Now the property can only be set in the constructor, and if we try to modify it somewhere else, it'll raise an error. Another useful modifier is the optional modifier. Let's say we add a nickname property to the class. For the user, it'll be completely optional. They can choose if they want it or not, so we don't want to set it in the constructor. To mark a property as optional, we just add a question mark after the name. And that'll also clear the error. We'll talk about how to safely change property values a little later on. For now, let's move on to Access Modifiers. Access modifiers specify if we can access properties or methods outside the class. In TypeScript, we have 3 access modifiers: public, private, and protected. Public variables and methods can be accessed outside their class. To set a method or property to public, we use the public keyword in front of its declaration. So we can do public in front of the name property, then go outside the class and change it to something else. But by default, the members of a class are all public, so we don't need to explicitly set it. If we remove the public keyword, we can still change the property. On the other hand, private members can't be accessed outside the class. If we set the name to private, we'll get a compilation error where we try to modify the name. The name property is private and only accessible within the employee class. So let's delete this. We can still access the name inside the class, so we can do something like this.name is walking. And let's invoke it to see it in the console. As a convention, we add an underscore in front of private members. The property is all over the place, so we'll click on one of them and press F2. This allows us to rename all the instances of it in the current file, with underscore name. Okay, our third modifier is protected. It's like private, so members can be accessed inside the class, but also any class that inherits from it. We'll cover the protected modifier when we discuss inheritance. For now, let's move on to parameter properties. Parameter properties allow us to simplify our property declarations. We can add an access modifier in front of a parameter, and this will tell the compiler to initialize the value. So we can do public for the ID, and private for the name. Then we can remove the declarations up here, as well as everything in the constructor body. Basically, we declare all our properties in the constructor's parameter list. So we can bring the nickname down as well. And if you remember, we had our ID as read-only, so we'll add that after the public keyword. And by convention, we add an underscore to private properties. This line is getting a little long, so let's break it up and put each declaration on its own line. Okay, from now on, we'll declare our properties directly in the constructor's parameter list. A getter is a method that we use to get the value of a private or protected class property. For example, we have an employee class with 2 private properties called first and last name. But, let's say we need to render the full name in the browser when the employee logs in. Well, in that case, we can use a getter. So we'll say get, then full name, which is going to return a string, and in the body, we'll return the concatenated names. Then we'll go down here and console log, employee1, full name. And it's a property, so we don't invoke it like a function. Now, let's say that our employee got married and wants to change her last name. Well, then we can use a setter. So let's go below the getter and say, set, last name, new last name, and in the body we change the last name. Now we can go down here before the console log and change the last name. If we save and take a look in the console, the new last name shows. Getters and setters are not only great to access and modify private and protected fields, but they also help us hide implementation details. TypeScript allows us to have properties and methods that belong to the class, instead of the object. As an example, let's say we have an employee tracker class. It has a property that tracks the amount of employees logged into the system, and two methods that add to or remove from that number. So let's create two new employees and log them into the system. Now let's log the active property to the console. If we save and take a look at the console, both tracking numbers show 1. Each object lives in a different place in memory, so they don't share the active property. When employee 2 logs into the system, it doesn't change the tracker in employee 1. This is the ideal situation for a static property. So let's add the static keyword in front of the active property. This is going to give us several compilation errors. Because a static member is on the class and not the object, we can't use this. Instead, we use the class name. So in the methods, we'll replace this with track employee. And we can do the same with the console logs. In fact, we don't need this second one anymore, so we'll remove it. If we save and take a look at the console, it shows both employees logged in. Now of course, the active property is public, so anyone can modify it directly. We only want the value to be modified by the login and logout methods. So we'll do private in front here. Then we'll go below the methods and add a public getter that returns the active property. But, because we're working with a static property, we'll need to make the getter static as well. And now, all that's left to do is change the console log to use the getter, instead of the property itself. If we save and take a look in the browser, the tracker still works as it should. Index signatures allow us to type objects with an unknown structure, but where we know the types of the keys and values. Let's say we have a ticketing application that allows users to book seats at a cinema. The seats are numbered A1 through 10, and goes further up the alphabet to G, also 1 through 10. The tickets themselves are numbered with some sort of unique number. So we know that the seat numbers should be strings, and the tickets should be numbers. We don't want to define individual properties, like B1 or G5. It's not only repetitive, but what if we add other cinemas later on that uses a different numbering system? This is where we can use index signatures to create properties dynamically. First we'll do square brackets, then give our dynamic property a name, like seat, and a type of string. But we also need to specify what type the value will be. In our case, the tickets use numbers as their unique identifiers. So, we'll go outside the square brackets and set the type to number. Okay, now let's create an instance, so, let seats equal new seat assign. Then we can do seat B1 equals the unique ticket number. And let's do another seats D7 unique ticket number. So, with index signatures, we can create dynamic properties with type safety. Inheritance makes it possible to reuse code from other classes. We can wrap common sections of code in one class, then inherit its functionality in another one that can extend that functionality to match its needs. Let's start by defining our parent class. Inside, we'll add a method called move, and just have it logged to the console. Our base functionality is move, because any type of animal can move. Now let's add another class called dog, and we'll say that it extends animal, so it inherits from it. Okay, without adding anything inside, we'll create a new dog object. And if we use the object, we'll see we have access to the move method, so let's select it. If we save and take a look in the console, we'll see the text. So the dog class has inherited the move functionality from animal. But it can also have its own functionality, so let's go into the dog class and add a method called growl. Then we'll go down here and invoke the method. And if we take a look in the console, we see the text from both methods. Now, something else all animals can have is a name. So, let's define one as a parameter property in the parent class constructor. We'll get a compiler error on the instance, saying that an argument for name wasn't provided. If a child class doesn't have its own constructor, we can just use the parent constructor when we create a new object instance. So, we'll add a name and the error goes away. But what if we need a constructor in the child class? Let's make one with another parameter property. Now we get a couple new errors, so let's start with the constructor. In TypeScript, we get a special keyword called super that we use to reference the base class. So we'll say super and parentheses to call the constructor of the parent class. And now we can see the parameter that we need to add, so we'll add it here. But we also need to add it in the parameter list above. Notice that we're not using the public keyword because we're just referencing the parameter from the parent, we're not declaring it. The object instance now needs to have another argument for the good boy parameter, so we'll add that in front. Now, earlier we mentioned that a child class can extend the functionality of what it inherits. So, let's say that we want to add the name to the console log in the move method, but we want to do it in the dog child class. We can modify the behavior of a method in the parent class by overriding it in a child. So we'll say, override, move, and in the body we'll do the console log again. If we save and take a look in the console, it shows the new text. What we just did is known as polymorphism. That's a big word, but basically, it just means having many forms. So, because we override the method, it has many forms. An interface is like a parent class with no implementation for its members. Instead, the child class has to provide that implementation. An interface is defined the same way as a class, except we use the interface keyword. Inside the code block, we'll define a method with one parameter and a return type, but not a body. It's up to the class that uses this interface to implement the body. So, let's make a class called Sparrow, and we'll say that it implements, not extends, flyable. And if we hover over the error, we'll see that property fly is missing. So we'll do fly, speed, and to keep things simple, we'll just do a console log in the body. Now we can instantiate an object of the class and invoke the method. And if we take a look at the console, the text shows as we expect. We can also implement multiple interfaces by separating them with a comma. As an example, let's duplicate flyable down, change it to hoppable, and the method to hop. We'll add it to the Sparrow's implementation list and duplicate the fly method to change it. Finally, we'll invoke it at the bottom. And if we save, we'll see the text in the console. Now let's say we add a name property to flyable. We'll need to initialize it with a value in the class, or use a parameter property in the constructor. Then we'll change the console logs to use the name. and add one where we instantiate the object. If we save and take a look at the console, we'll see that Zippy flies and hops, so everything works like it should. The final point to note is that interfaces can extend other interfaces. So we can do something like hoppable extends flyable. Then down here in the class, we can implement only hoppable, and everything will still work fine. A generic is essentially a function template and allows us to define placeholders for its types. As an example, let's consider these two functions. Both functions have the exact same logic, the only difference is that one returns a number and the other returns a string. So instead of having two functions, we can define a single generic, and let the developer that uses it choose which type they need. Let's remove everything up to the first function. We're leaving it as a reference while we build the generic one. Now let's define our generic, so, function, logger, and then we add a pair of angle brackets. Inside the brackets, we add what's known as a type parameter. A type parameter can be any letter or word, but the convention is to use T. This comes from C++, where generics are called templates, and use the T. This T is what we're going to use to specify the type when we call the function. So let's just add the parentheses and curly braces, then go below it and say logger. Now here we have to add the angle brackets again, and specify the type we want, like number. Now we can use T in the function wherever we want the same type, like the message parameter. So now in the function call, we'll have to use a number, like 30. If we try to add a string, we'll get a compilation error. Just like with the parameter, we can use T as a return type, and then we can return message. At this point, it's exactly the same as the function at the top. But now we can call the generic again, this time with a string as the type. Okay, but we want the generic to actually log the message to the console, so let's change the return type to void, and log the message to the console. And if we save, we'll see both get printed. Just to demonstrate that other types can be used as well, we'll do another logger with a boolean that's true. Okay, everything works like we expect. Let's remove this top function, we don't need it anymore. Let's say we want to limit the types in our generic function to only numbers and strings. To do that, we use the extends keyword. So let's go in the angle brackets and do T extends number, or string. Now we'll get a compilation error on the boolean, saying that it doesn't satisfy the constraint, so let's remove it. And by the way, TypeScript can infer the type we want from the parameter, so we can remove these, and if we save, we'll see everything still works fine. We're not limited to using just primitives, we can do something like an object with a name of type string. Now we can only pass objects that conform to this specific shape. We can also do classes and interfaces, so we'll go up here and define a class called animal. Then we'll do a parameter property called name. And constrain the generic type to animal. In the function call, we'll do new animal, Mickey Mouse. This works, but we can also do classes that inherit from animal. So let's create a new class called dog that extends animal, and we'll do another function call with a new dog, Goofy. We're not limited to only generic functions, we can have generic classes too. As an example, let's create a custom key value store. So, let's remove all this and do class key value store, and like with functions, we specify the generic type in angle brackets after the name. This time though, let's do two types, with T and U. In the body, we'll add a constructor, then public key as T, and public value as U. Okay, let's instantiate a new key value store. Then we'll specify the types we're using, so let's do number for the key and string for the value. And finally, we'll initialize the object with a number and string value. Now, like with functions, we can omit the types if we're initializing the object with values. To demonstrate that it works, let's console log the key and value. Okay, it works just fine. That's it for this TypeScript course, we hope you found it useful. Thanks for watching, and don't forget to subscribe for more tutorials.